Okay, so welcome everyone. Welcome everyone to week 6 of our NPTEL-PMRF problem solving sessions. Just 1 minute. Alright. Okay, so welcome everyone to week 6 of our NPTEL-PMRF problem solving sessions for this course Electronic Theory of Solids. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structure Chemistry Unit, SSU of the Indian Institute of Science, IC Bengaluru, India. And I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering. And I am an NPTEL PMRF TA for this course. Okay, just 1 minute. Okay, recording is okay. So let's just start with our today's session. All right. So first of all, we will start with. Let me just check if. Okay. So first we will start with a tight bending problem from week 5. Let me just get this. Let me make this first. Okay, just 1 minute. Alright. So in today's session, let me just check once. Sorry about it. Just check if recording is okay. All right. So in this session, so first we will start with the one of the problem from week 5 that we were doing in tight binding model. So this was the problem. So in this problem we have to determine the energy dispersion relation for simple cubic structure, body centered cubic structure, BC structure, and FCC structure using the nearest neighbor tight binding approximation. So we had completed this part A. So part A was completed, and in this session we will complete the remaining B and C part. So first of all, so just a recap of what we did. So basically, this is the how we can write our wave function in the linear combination of atomic orbiter approximation, LCAO approximation. So from LCAO we can write our wave function like this. Then we have our k vector as kx, x cap, ky, y cap, kz, z cap, and our r vector, which is the lattice vectors, real lattice vectors. Right. So we have those. We have that r vector, capital R vector. So from there we calculated our wave function side. We can do k vector dot r vector. If we do, then it will be k vector dot a1 vector, k vector dot e2 vector, k vector dot e3 vector times this wave function of the atomic orbiters, which will be denoted by m and l. So we had done several problems in the last session on tight binding model, and what we did was each of these sides we denoted by the indices, and since we are in 3D, like in 1D, in 2D we denoted it by mn, and this was the 3D problem, so we denote each index by m and l. So the atomic orbiter at each of this index will be given by psi m and l. Then the energy dispersion, it is just given by this integral. Alright, and here dr vector was dx, dy, dz. So we put our wave functions here, and then if we do this integral, then we reached this expression. So energy dispersion 1 by n summation of m prime, n prime, l prime, m and l times this e k vector dot a1 vector m minus m prime, e k vector dot a2 vector n minus n prime, and same for the e to the power iota k vector dot a3 vector l minus l prime times this matrix kind of element, which we know is basically just this integral. So this we know is just dr vector psi m prime, n prime, l prime star r vector h cap psi m n l r vector. Okay, so there is, so this in that Dirac notation we can denote this integration like this. Then we solved the problem for the simple cubic, in which first of all we started with, like, there are six nearest neighbors and a1, a2, a3 vector were given to us. Then accordingly to a1, a2, a3, if we start with M and L, then we define all the other six coordinates, the indices for the other six coordinates. Then we just using a1, a2, e3 vector is given to us, we can write our energy dispersion now like this. Okay, then the procedure was, we correct the non-zero terms. Since there are six nearest neighbors, so we will have seven non-zero terms. One will be the self term and the other will be the accordingly to the six nearest neighbors. So according to the six nearest neighbor, we can find all these terms, and then we can find our energy dispersion. Just putting in the values, we found our dispersion relation. Okay, like this. And then here we can see that, okay, so this was our energy dispersion relation for the simple cubic case. And here we can see that to find the bandwidth, whatever the maximum value of this minus the minimum value, so that we can see it is 12 times of t. All right, so now so that there were two remaining parts. One was for the BCC body centered cubic case, and one was for the face centered cubic case. Okay, so now we will start our B part. Let me just check. So we're doing, we did the A part. Okay. Alright. So let's just start with our part B. So in B part, we have to do it for the body centered cubic PCC. Alright. So for this we have to solve, and so again here we have 8 nearest neighbors. Okay, and the lattice parameters for this BCC, they are given by a by 2 x cap plus y cap minus z cap. E2 vector will be equals to a by 2 minus x cap plus y cap plus z cap, and a3 vector will be equals to a by 2 x cap minus y cap plus z cap. Alright, so now for the body centered cubic, basically the structure is given like this. So we will have this. I can just make one unit cell here, and then alright, and then one we have at the center, let's say here. Alright, so I will now denote them, and let's say these are our this is my x-axis, this is my y-axis, and this is my z-axis. Okay, so these are our atoms here in this system. Okay, so this is the atom. So let's say again when we denote this atom as MNL. Okay, this is our, let's say, MNL coordinates. Okay, and our E1, E2, E3 vector, they will be given like this. So I will have an E1 vector. So accordingly, the nearest neighbor, basically they are going to be 8 nearest neighbors. So how we, for the body centered QE, we have this MNL 1, and if you take an E1 vector, will be along this direction. Then your E2 vector will be along this one. This will be your E2 vector, and correspondingly this will be your E3 vector. So along the E1 vector, you will have your first neighbor. So its coordinates will be just m plus 1 comma n comma l. So m and l, that is so basically it is m plus 1 times E1 vector plus n times E2 vector plus l. Basically, sorry, from m and l you are going to m plus 1 comma n comma l. So basically you just it is just m plus 1 minus m, which is 1 times of E1 vector. Alright, 1 times of E1 vector, you get to this neighbor. So its coordinates are m plus 1, and similarly you will have in the opposite direction as well. So this neighbor coordinates will be m minus 1 comma n comma l. Then similarly this neighbor we can go through by E2 vector. So it will be m n plus 1 comma l. Okay, 1 minute, I guess with this m minus 1 comma n comma l. This will be m plus 1 comma n comma l. So coordinate for this neighbor will be m comma n plus 1 comma l. Then correspondingly we will have one in the negative direction. So it will m comma n minus 1 comma l. Then for this one, the coordinate will be m comma n comma l plus 1, because we can go from m and l to this using E3 vector, and correspondingly we will have one in the negative direction. So m comma n comma l minus 1. Alright, and then the remaining two ones. This one, okay, this is done. Okay, this one is remaining. So this we can reach by, if you check, it is m minus 1 comma n minus 1 comma l minus 1. So basically taking using all the three coordinates. So basically using all the three coordinates, you can see that if we use all the three lattice parameter, then we will go to this point, which is m plus 1 comma n plus 1 comma l plus 1, and similarly in the negative direction we will reach to this point and this point. Okay, and this point coordinate will be m minus 1 comma n minus 1 comma l minus 1. So these are the these are the coordinates for our neighbors. Alright, so now first we will write our energy dispersion relation using the E1, E2, E3 vector that we have, and the formula that we have derived in the previous class. So using the formula that we derived in the previous class and the E1, E2, E3 vector for BCC, we can write this as 1 by n summation our m prime, n prime, l prime, summation our m and l. We have e to the power iota a by 2, it will be kx plus ky minus kz. So it is a1 vector dot the k vector, that will give you, and from there we get m minus m prime. Then I will also have e to the power iota a by 2 minus kx plus ky plus kz times n minus n prime, and then you will have e to the power iota a by 2 kx minus ky plus kz times l minus l prime. Then we will have our this integral m prime n prime l prime h cap m and n. Alright, so this is the expression basically. This is e1 vector dot k vector, e2 vector dot k vector, and then e3 vector dot k3 vector, e to the power iota that, and then we have this expression. Okay, now we have to correct the now the same strategy, we have to correct the non-zero terms. So now correct the non-zero terms. Alright, so since there are 8 nearest neighbors, there will be 9 non-zero terms from this summation, and as we have said, there will be n times of this non-zero term, so that n in the denominator will be cancelled out from there. So first we will get for m prime n prime l prime, it is equals to m n and l. In that case, basically in that case all these epsilon terms will be 1, it will be e to the power 0, okay, because m prime will equals to m, n prime equals to n, l prime equals to l, and this this integral term, m and l, h cap m and l, that is the self energy epsilon naught, some constant. Then next will be now our first neighbor, which will be m plus 1 comma n comma l. So then what we will have m plus 1 comma n comma l, h cap m and l, right. We have this integral times, so n and the exponential with n l l, they will be just 1, and we will have one exponential e to the power minus iota a by 2 times kx plus ky minus kz. Alright, so and this we know it is our this hopping term, so it will be minus t times e to the power minus iota a by 2 kx plus ky minus kz. Alright, then our next neighbor is l prime. Now that will be equals to m minus 1 comma n comma l. So again we will get m minus 1 comma n comma l, h cap m and l times e to the power iota a by 2 kx plus ky minus kz. Okay, the one with the n and l will cancel, and now instead of minus iota we will just have a plus iota here, and this will be written as minus t e to the power iota a by 2 kx plus ky minus kz. Right. Then fourth one, they are going to be in terms of m comma n prime comma l prime. So this will be now next neighbor will be m comma n plus 1 comma l. So that will be m comma n plus 1 comma l Hamiltonian m comma n comma l times e to the power, the m and l exponentials will be 1, and the one with n that will survive, and it will be to the minus iota a by 2 minus kx plus ky plus kz. Alright, so this will be equals to again minus t e to the power minus iota a by 2 minus kx plus ky plus kz. Then next term, so we are going to have total there are 9 terms. So the fifth term will be an m prime, n prime and l prime will be other neighbor, which is n minus 1 comma l, which will be m comma n minus 1 comma l, h cap m comma n comma l times e to the power, now it is e to the power iota a by 2 minus kx plus ky and plus kz. This is the similar same term, but now with a positive sign here, because we have n minus 1. We have minus t e to the power iota a by 2 minus kx plus ky plus kz. Alright, and the sixth term will be m prime comma n prime comma l prime. It will be m comma n comma l plus 1. So this will be m comma n comma l plus 1 h cube Newtonian m comma n comma l e to the power. Now we will have minus iota e by 2. So okay, now let us not or maybe let me just write later maybe that's the point. L e to the power minus iota a by 2. It will be kx minus ky plus kz. So it will be minus t e to the power minus iota a by 2 kx minus ky plus kz. Alright, and similarly now we will have the seventh term m prime n prime and l prime, m n and now l minus 1 neighbor. So there will be m comma n comma l minus 1 h cap m comma n comma l epsilon to the power. This will be negative, so this will be positive now, e to the power iota a by 2 kx minus ky plus kz. So this will be minus t times e to the power iota a by 2 kx minus ky plus kz. And then we have our eighth term. Now the remaining two terms will be for those two neighbors on the like body diagonal, which are formed by all the three vectors. So one will be for m comma n comma l plus 1. It is m plus 1 comma n plus 1 comma l plus 1. Right. So using all the three vectors. So this will be, again you will have this integral m plus 1 n plus 1 comma l plus 1 h cap m comma n comma l, and then epsilon. If you sum up, basically each of them will give you a minus iota a by 2 because each of them will be a negative value. So these terms, it was e to the power iota a by 2 m minus m prime, and you are using m prime as m plus 1, n prime as n plus 1, and l prime as l plus 1. So we get e to the power minus iota a by 2 from each one of them, and all the k stuff that we just add up. So let me just write here kx plus ky minus kz plus you will have, so one will be this. Let me just write it like this. So it will be from this m minus m prime term. Then you will have minus kx plus ky plus kz from the n minus n prime term, and then you will have kx. Next will be kx minus ky plus kz. Right. Okay, so that will be equals to minus t times e to the power minus iota a by 2, and if you see, it will be just kx plus ky plus kz. Right. And then the last ninth term, which will be for our last neighbor, which is m minus 1 comma n, which has the coordinates m minus 1 comma n minus 1 comma l minus 1. So for that I am just writing now the direct answer. So we know that there will be a hopping term, so that will be first I am writing it till now, so let me just complete it. H cap m comma n comma l, and then this will be just opposite to it. It will be just e to the power iota a by 2 times kx plus ky plus kz. This you can check. And this term, this will be again, this will be the hopping term. So what we get, minus t e to the power iota a by 2 kx plus ky plus kz. Alright, so now we have all our non-zero terms. So now we can write our dispersion relation. So our dispersion relation is basically going to be equals to the summation of all these non-zero terms. So that will be equals to, we will have an epsilon naught, and then you will have a minus t. Then we will have all this summation, I will just write e to the power minus iota a by 2 kx plus ky. So, let me just write them in this thing, e to the power minus a by 2 kx plus ky minus kz, and correspondingly we will have like basically a complex conjugate of it, e to the power iota a by 2 from the this is from the m plus 1 neighbor, and then we have for m minus 1 neighbor we will have a complex conjugate, which is minus kx plus so 1 minute. It will be e to the power kx plus ky, it will be kx plus ky minus kz. Alright, so this could be our one of the terms. Okay, let me just, okay, so this I will take as one of the terms. Then similarly I will have e to the power minus iota a by 2 from n plus 1 neighbor minus kx plus ky plus kz, and then I will have a complex conjugate from the n minus 1 neighbor minus kx plus ky plus kz. Okay, so this we have seen already. And then we will have again we will have this one from the l plus 1 neighbor kx minus ky plus kz, and then the complex conjugate of it from the l minus 1 neighbor kx minus ky plus kz, and then we will have one from the both m plus 1 n plus 1 l plus 1 to minus iota a by 2, that will be kx plus ky plus kz, and then the complex conjugate of it from the m minus 1 n minus 1 and l minus 1 neighbor, e to the power iota a by 2 kx plus ky plus kz. Alright, so basically we have 8 terms from the neighbor, and then we can combine, we can do this combination of each of these, like in the brackets you can see 1 2 3 4, each one with a complex conjugate, and you know that e to the power iota cos theta plus iota sin theta. So just using that we will get from each of them we will get a 2 cos theta kind of term. So we can write this relation as epsilon minus 2t cosine of kx of a by 2 plus ky of a by 2 minus kz of a by 2, kz times a by 2 plus so there are going to be like we had 8 terms, so there are going to be 4 cosine terms, minus kx a by 2 plus ky a by 2 plus kz a by 2 plus next cosine term kx a by 2 minus ky a by 2 plus kz a by 2 plus last cosine term, which will be kx a by 2 plus ky a by 2 plus kz a by 2. Alright, then to like this is a cosines with this 3 thetas you can say, so you have to use this relation. So this relation use cos of a plus b plus c, so that is given by cos a cos b cos c minus this is a trigonometry relation that you have to use. Basically, finding the energy distribution from tight bending, most of the time it is just realizing the e1 e2 e3 vector, then and finding the coordinates of the neighbors. Then at the end always we will get something in the cosine forms, and then it is all just trigonometry. Sin b sin c cosine of a minus sin a sin c cosine of b, sin a sin c cosine of b, and minus, so you have to use one of the, you have to use actually two relations. So one of the relation is this cosine of b, and minus sin a sin b cosine of c. Okay, let me just check those. Cos a plus b is cos a cos b cos c, minus sin b sin c sin a cos a, minus sin a sin c cos b, minus sin a sin b cos c. Okay, and also just this relation as well, that you already like, the sin of minus theta will be minus of sin theta. Alright, so you have to use these two trigonometric relations for this 4 cosine terms, and if you use it, then so now I'm just going to write the final answer. So basically what will happen if you I can show you, like, for what will happen if you when you open this using cos a plus b plus c, then you can see that cos a cos b cos c, then you will have some this sin theta, because some of them will have a minus terms, so most of the terms will just going cancel out. So each of these 4 terms will open into this 4 terms, like 1 2 3 4, so like you are going to have like 16 terms, but most of those terms will cancel out because sin of minus theta will be sin theta. And here you can see you have some minus values here, like minus of kz a by 2. Okay, so that will give you some sin of minus kz a by 2 will be minus of sin kz a by 2. So you can check it. It's a little cumbersome, but you can try to do it. So basically, if you just use these two relations here for the cosines, your final answer will be kx comma ky comma kz, that will be equals to epsilon naught minus 8t cosine of kx a by 2 cosine of ky a by 2 and cosine of kz a by 2. Alright, so this is going to be our final answer for this is the energy dispersion for the body centered cubic structure. Alright, so next let's move on to the C part, our last part, which was the face centered cubic case, FCC. Okay, so so here we have here, so, okay, let me just write in purple. Right, the C part, let me just use this one. So we have face centered cubic case. Alright, this is the face centered cubic case, FCC. Okay, now here we have, here we have 12 nearest neighbors. Okay, so for FCC you are going to have 12 nearest neighbors, and we have A1 vector will be equals to a by 2 x cap plus y cap. So basically the formula that we have derived for the energy dispersion for the 3D case, for that you can just take that formula, and then you just need, for any 3D structure, you just need these lattice vectors. What are the lattice vectors? And then how many nearest neighbors are there, and then you need to find the coordinates of this nearest neighbors. Alright, so these are the parameters. Okay, x cap plus e2 vector y cap plus z cap, and e3 vector a by 2 x cap plus z cap. Right, then for a simple cubic for a face-centered cubic. Okay, for a face-centered cubic, let me just check if I have written all the neighbors. Okay, so for face-centered cubic, it is difficult to actually show you all the neighbors here. So let's say if you have x, y and z coordinates, so just form your FCC structure. If you form one center here, one center here, one here, one here, one here, and one it's here. And let's say you start with this one. Okay, then the a1, a2, a3 vector that are given to you, they will be along this direction. So one will be along a1 vector, so one neighbor will be this face-centered neighbor, one will be this in this direction, so one neighbor will be this face-centered neighbor, and one will be in this direction. And as you can see, if you make the periodic boundaries, then as we know, one neighbor is along the minus a1 direction, so one neighbor will be around minus a2 direction as well. And that you can see if you have like periodic images of this. So showing it in 2D for FCC case is quite difficult to show all the 12 nearest neighbors, but you can imagine basically the same thing, like along the a1 vector we can see, like, okay, this is this 3 I can show here within this unit cell, nearest neighbors along the a1, a2 and a3 direction. And similarly, by combination of a1, a2, a3, you can find other nearest neighbors as well. So in this case, I will just give you the coordinates and just quickly solve this, because there are going to be 12 terms, 13 terms basically, so it's quite difficult to it will take a lot of time to solve it properly. So basically there are going to be 12 neighbors, and you can find those neighbors by a combination of is a1, a2, a3. Alright, so okay, and the energy dispersion relation, this now will be equals to m prime, n prime, l prime, m and l. From k vector dot a1 vector, it will be e to the power iota a by 2 kx plus ky times m minus m prime, and e to the power iota a by 2 ky plus kz n minus n prime, and e to the power iota a by 2 kx plus kz into L minus L prime, and then you will have the integral m prime, n prime, L prime, h cap, m and L. Alright, then the same strategy, correct the non-zero terms. Now since there are 12 nearest neighbors, there will be 13 there will be 13 non-zero terms. So I can write it as m. So one term will be no is the self energy. So now yeah, I'm just writing exactly what are the terms are. Or let me just write what are m prime, n prime, n prime. So m prime, n prime, l prime is equals to just m and l. Then you will have the term epsilon naught. Okay, so the integral will be just epsilon naught. Then you know the whatever the Dirac form of that integral is. We'll just continue with this thing. Okay, so basically it will be m and l h cap m and l equals to epsilon naught. Then your m prime. Now the second and third terms, since we have seen in the in all this example that there will be one term and then there will be a complex conjugate term. So basically that I am doing now. So there will be, I am writing two terms now together. So there could be m plus minus 1 and l. Okay, 1 to with the even vector 1 to the e2 vector. So you will have this m plus minus 1 comma n comma l h cap m comma n comma l times e to the power minus plus. Okay, for plus m plus 1 there will be, because it is m minus m prime, it will be e to the power minus, to minus plus iota a by 2 kx plus kz. Alright, so that will be just minus t times e to the power minus plus iota a by 2 kx plus kx plus kz, right? Kx plus ky, sorry, is it kx plus ky? Sorry, it is kx plus ky. Alright, and similarly we can write the fourth and fifth term. Okay, now the fourth and fifth term will be just even where m prime, n prime and l prime is m comma n plus minus 1 comma l. So now yeah, we'll just write the minus t directly. Okay, you know whatever the integral is, that is going to be Hoping integral by now. So all the neighboring terms, the integral will be minus t times whatever the exponential is, and the exponential will be minus plus iota a by 2. This will be ky plus kz. Then similarly we have sixth and seventh term. So sixth and seventh, for sixth and seventh term it will be m prime, n prime and l prime equals to m comma n comma l plus minus 1. So we get minus t e to the power e to the power minus plus iota a by 2 kx plus kz. Right, it is kx plus kz, right? Ky plus kz and kx plus kz. Alright. Then we will have 8th and 9th term. Okay, now 8th and 9th term, for this we will get from m prime, n prime and l prime. If they are equals to you get an m comma n plus minus 1 and l minus plus 1. Okay, so this I would like you to check. Okay, so one neighbor would be given by taking n plus 1 and l minus 1 coordinates. So that will give you minus t times e to the power minus plus iota a by 2 ky plus kz and e to the power plus minus iota a by 2 kx plus kz. Okay, just taking basically both of the terms from the exponential will be there. So both these two terms exponentials will be there now. minus was n plus minus because we have L minus plus. Then you will have 10th and 11th term. So we know that the neighboring terms will always be in even, and we will always have one term and its complex conjugate. So we have n prime, L prime. There will the next neighbor will be m plus minus 1. M plus minus 1 comma n comma L minus plus 1. So that will give you minus t e to the power minus plus iota a by 2 kx plus ky and e to the power plus minus iota a by 2 kx plus kz. And then we will have the last two terms from the neighbor, terms 12 and 13, where we have m prime, n prime and L prime given by m plus minus 1 comma n minus plus 1 comma L. Alright, so this gives you minus t times e to the power minus plus iota a by 2, that is put on kx plus ky, and then we have e to the power plus minus iota a by 2 ky plus kz. Alright, so again you have to do the same thing. You just have to sum up all these 13 terms, and the same thing will happen. We will have complex conjugate for, so for each of these like two terms that I have given together, like 12, 13 term, 10, 11 term, you will get a cosine of whatever you have here. Okay, so you can find this cosine and sine. So this is all trigonometry. It's better to do in computer, so to be honest. Okay, so most likely no one will ask you to do it by hand, but it's a nice thing. Okay, you know this thing, now you can just compute that thing. You can just put it write a code for this thing in the computer, and if you solve it, then for FCC basically you just have to sum up all these 13 terms. You will get epsilon minus 4t cosine of ky a by 2 cosine of kz a by 2 plus cosine of kz a by 2 and cosine of kx a by 2 plus cosine of kx a by 2 and cosine of ky a by 2. Okay, ky a by 2, kz a by 2, kz a by 2, kx a by 2, kx a by 2, ky a by 2. Alright, minus 4t. Alright, so this will be our final energy dispersion for the face centered cubic case, where we have 12 nearest neighbor. So this was our last problem on type binding wonder. Basically the take home messages from this problem, from this 3D problem, was that this formula basically, so you have to use this formula. So this is an important formula that we derived. So basically from this, if you have this equation, then you just have to put your lattice vector a1 into a3, put them in, and then just find the coordinates for your neighbors in terms of this MNL, like we have done for all these three cases, like simple cubic, BCC, and then for this FCC cases. Alright, okay, so this was from last week, from the last week 5 session. Okay, so let's start with some other problems. So mostly we will do some problems on magnetism, and the rest of the session we will do most of the problems, they are from magnetism only. I guess all the problems are from magnetism. Okay, so the first problem is the free energy of a ferromagnet close to a transition is given to us. Okay, which is F is given by this F naught times A naught T minus Tc m square plus B times m to the power 4, where F naught, A naught and B are some positive constants, and M is the magnetization, and T is the temperature, and Tc is our Curie temperature. So we have to find the relation between M square and T, and also provide a proper and also provide a plot for it. Okay, so this is the problem that we have. So here here I can write, okay, we have F is given by F naught plus A naught times T minus Tc M square plus B times into the power 4. Okay, so first of so we know that first what we do, we will take a derivative of this free energy, so that will be 2A naught T minus Tc times M plus 4B M cube. So first we need to find the relation between this M square and T from this free energy. Now basically we know if we try to minimize this free energy for the ferromagnet, so minimizing free energy of ferromagnet occurs when del F by del M is equals to 0. Okay, so this derivative is 0. So we just we just put this del F by del M, okay, which is equals to 2A naught times T minus Tc times M plus 4B M cube. I will put it to 0. So what we will have 2A naught T times T minus Tc plus 4B M cube times M, that is equal to 0. Now since M cannot be 0, therefore first part must be 0. Okay, so the first part here, that must be 0. Alright, so that gives us 2A naught T minus Tc plus 4B M square is equals to 0. So here M square will be equals to minus of 2A naught T minus Tc by 4B. So fine, so now we have our relation of M square versus T. So M square will be equals to minus A naught upon 2B times T plus A naught upon 2B times Tc. Okay, so this is our solution, basically the relation between M square and T, and here we can see that basically this is a straight line. So if we do a plot M square versus T, then this will be a straight line, like, okay, with a negative slope. So the slope is minus A naught upon 2B, and this intersection, that will be our Curie temperature Tc. Alright, so by plotting for a ferromagnet, by plotting this kind of plot of M square T, we can easily find the Curie temperature for that ferromagnet. Alright, so this was our problem number 1. Problem number 2 for this session. Problem number 1 was the type binding problem. Okay, just 1 minute. Okay, so the next problem is okay, so it is given that potassium matter has electron concentration of 1.4 into 10 to the power 28 per meter cube, and the corresponding density of states at Fermi level, that is also given to us. And if the polymagnetic susceptibility of potassium is given to us, so the magnetic susceptibility is given to us, then we have to find the value of K. Alright, so for this problem it is given like what we are given is, we are given the electron concentration is given to us, which is 1.4 into 10 to the power 28 per meter cube, and then the density of states at the Fermi energy at the Fermi level, that is given to us 6.2 into 10 to the power 46 joule inverse per meter cube. Alright, and we know the Bohr magneton nu b, or as a magnetic moment of a single electron, that is 9.3 into 10 to the power minus 24 joule per Tesla, and then nu naught, the permeability is given as 4 pi into 10 to the power minus 7 T, it is Tm per ampere. Okay, these are all in SI units, so you don't have to worry about the unit conversion. So now we know that this chi of a polyparamagnetic susceptibility of this for basically polymagnetic susceptibility, that is given by nu naught nu b square times the density of states at the Fermi energy. So you just have to put in the formulas and unit values in this formula, and then you will get 6.735 into 10 to the power minus 6. So just comparing with it, okay, we want 6.735 minus k, so the value of k will be equals to 6 here. Okay, so you just need to remember that the polymagnetic susceptibility is given by this formula, nu naught nu b square times the density of state at the Fermi energy. Okay, so this was our problem number 3. So let's move on to problem number 4. Okay, so what is given to us? What is the value of the commutator E cap comma P cap if this gradient dot product of this gauge potential E cap with this gradient, that is 0, and this the divergence is 0, where E cap is our gauge potential and P cap is momentum. Okay, so we have to find this commutator relation. So the commutator, we have to find what we can do E cap comma P cap acting on some side. We will act this commutator on some side. It will be minus iota h cross E cap. So this will be basically, okay, let me just write it from the start. That will be A cap P cap minus P cap E cap acting on cat psi. Now P cap we know is minus iota h cross times gradient. So we have A cap dot this gradient minus gradient dot E cap times psi, and this is given to us that divergence of E cap, that is 0. So what we'll have here, minus iota h cross E cap dot divergence of psi minus divergence dot E cap psi. Let me just write it with these brackets. Now if we do that, what we will have E cap dot divergence of psi. Now this divergence will act on this will give us psi times divergence of E cap and minus E cap divergence this gradient of psi dot, right? and this is given to us this is given to us divergent dot a cap is equals to 0. So this term will be 0, and then the other two terms you can see that there is a cap dot gradient of psi. So what is remaining is minus iota h cross a cap dot gradient of psi minus a cap dot gradient of psi. So that will be 0. So that's why this gauge potential will commute with our momentum operator. So e cap comma p cap, this commutation, this e cap p cap minus e cap p cap, that will be equals to 0. Okay, so the gauge potential that we use, it will commute with the momentum operator. Okay, so this was our problem number 4. So let's move on to problem number 5. So problem number 5 is what are the values of spin s, orbital L, and total angular momentum G respectively. So okay, so the rest of the problem they are all on Hund's rule. So so the rest of the problems that we are going to do, they are all on Hund's rule. So first of all, we have what are the values of spin s, orbital L, and total angular momentum G respectively for iron, for which Z is given to us as 26, which has more than half-filled 3D shell with 6 electrons. So in this problem, it is so it is given that we have to find it for iron, and the main point here you need to remember is that it is given that which has more than half-filled 3D shell with 6 electrons. Now for D shell, we know that for D, L is equals to 3. So basically, if we have this LZ or ML, whatever you want to call it, so that will go from plus 3, plus 2, plus 1, 0, minus 1, minus 2, and minus 3. Okay. Now it is given that the 3D shell. Okay, and also we don't need to care about the other shells, like it is Z equals to 26, so there are 26 electrons, but since it is written there, and also there will be one more problem on iron Fe plus 2 ion that we will do in today's session. So there I will show you the electronic configuration as well. So all the other electrons, they have already been paired, so they will give S equals to L equals to J equals to 0. So we don't care about them. We just care about this outermost electrons, which are 6 here. So which are some of them are unpaired. So they are going to give us some LJS value, and all the other electrons, all the remaining 20 electrons, which will be in this 2s 1s 2s 2p orbitals, or 3 and the 3s orbital, 4s orbital as well. We have 1s 2s 3s 1 there will be 1s 2s 2p 3s 3p and 4s orbital as well, but all of them will be filled. So those 20 electrons, they are not going to contribute to this. So let me just draw like if you maybe just put in perspective. So the electronic configuration of iron. So we do a lot of problem today, electronic configuration. So for iron it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d okay, 3p6, we have 3d6, 4s2. Okay, basically we actually write it as 4s2, 3d6. Now here now for iron, okay, so here you can see that all these other electrons, they are all completely filled. Okay, they are completely filled. So L, so if we calculate S, L, and G, okay, all these orbitals, they are completely filled. So S, L, and J values, they are going to be 0. So to find the total L, S, and J for this iron atom, we only need to take care of this d orbital electrons only, and that is what is given in this problem as well. That's why it just gave you the information regarding this 3D shell only, because that is only you need to find this thing, to find the value of S, L, and J. Now the 3D shell has 6 electrons, which is more than the half filled case, which is more than half filled. So J will be given by L plus S. Okay, so it will be given by L plus S. Okay, you can take the mod L as well. Mod of L. Now by Hund's rule, there are 5 electrons of same spin orientation and 1 electron with opposite spin orientation. Okay, so basically now we have to fill it according to the Hund's rule. So I will start with filling the spin up electrons. So first we will fill up the spin up electrons. We have we have 3D shell with we have 3D shell SPD. Okay, sorry, my mistake. I don't know why I did. Okay, so for L is equals to 2 actually here. Okay, okay. Sorry, my bad. For D equals to for D L is equals to 2. So it will be from plus 2, plus 1, 0, minus 1 and minus 2. Yeah. For D this L is equals to 2. So the LZ or the ML values. Okay, this could also be called ML as well. Sorry. Okay, so we have this plus 2, plus 1, 0, minus 1, minus 2. So first I will start filling the spin up electrons. So will be 1, 2, 3. Okay, by Hund's rule, as you know, first you need to maximize the value of S, and the maximum value of S will be when we will have the parallel spins. So we take the plus half value, because we need to maximize the value of S. So we take the plus half values, we fill the plus half electrons first. So just spin up electrons. So I fill all the spin up electrons. Now because of the Pauli exclusion principle, I could not fill any more spin up electrons. So I have to go with spin down electron. So wherever I will put this spin down electron, the value of S will be the same. So we will go to the rule number 2 of Hund's rule, which is maximizing the value of L, and the maximum value of L will be there when we will put it in the highest, because capital L is basically summation over this LZ or ML values. So here to maximize this, I have to put my spin down electron in the maximum LZ value. I will start putting it from the maximum to the negative values. Then okay, so this is how we go from we use the Hund's rule. Okay, so by rule 1, rule 2, so this will be the electron, how the electrons will be distributed within this D shell using the Hund's rule. So according to this, by Hund's rule, we will have this kind of spin, and that is what written here. We will have 5 electrons, 5 spin up electrons with parallel spins and 1 spin down electron. Okay, so that's why. So our S will be equals to, I will have 5 plus half electrons and 1 minus half electrons. So we just do a minus here. So that will be equals to 2. And the L value and the orbital angular momentum is capital L. So L is basically given by summation over LZ. Okay, we just have to sum up all the LZ values. So that we can see here, from all the blue ones, there will be plus 2, plus 1, minus 2 and 0. All the values will get cancelled out. So only value that we will get is from the spin down case. So basically you will have a summation over Lz for the spin up electrons, and then you will have one from the spin down electrons. Here the spin up will give you 0. Okay, so only contribution will be from the spin down one, which will be +2, because we have just one spin down electron only. Okay, so L will be equals to 2 here, and therefore the J value, that is equals to L plus S in this case, because it is more than half filled. So that is the Ohm's third rule. So by Ohm's third rule, J is equals to mod of L plus S, because it is more than half filled. Okay, because it is more than half filled, so it will be 2 plus 2 equals to 4. So this will be our answer. S equals to 2, L equals to 2, and J is equals to 4. Alright, so this was our problem number 5. Okay, let's go to problem number 6. So in this we have to apply the Hund's rule. Okay, so in this case we have to apply the Hund's rules to find the ground state of all these different ions and atoms. Okay, so let's just start. So first case we have Tb3 plus. So Tb3 plus has 4F8 configuration. So in this case we have L equals to 3. Okay, in this case we have L equals to 3, and here we have L equals to 2 for D case, for the D shell. So for F we have L equals to 3. So for L equals to 3, now again L mix boxes. Lg value we go from +3, +2, +1, 0, -1, -2, -3. Alright. Now again, according to the Hund's law, we will start filling the electrons within this F shell. So we have 8 electrons. So first, since there are like 3, 4, 5, 6, 7 shells. So first we will fill all of them with spin up. Right, all of them will be filled by spin up, because we want to maximize the value of S. That is most important. Okay, so first we will follow the rule 1. So we will just maximize the value of S. We will put one spin up electron in each of them. So now because of the Pauli exclusion principle, we cannot fill any more spin up electrons now, and we are still left with one electron. So that has to go into spin down case. Then we will go to the, now wherever I put this spin down electrons, the value of capital S is not going to change, it will be the same. Then we will go to the Hund's second rule. So Hund's second rule say that to maximize the value of capital L, and capital L is basically the summation of Lg, and to maximize the value of capital L, we need to fill the electrons in this sequence, from going from the most positive value to the most negative value, because we need to maximize the value of capital L. So yeah, we'll just put my spin down electron here. So my capital S value now, capital S value will be equals to, first we will have how many spin up? We have 7 spin up electrons, 7 times half, and then we have 1 spin down electron. So 1 times minus 1 times half, or it is basically you can write it as so I am writing it like this, but you can write it as plus 1 times minus half. Okay, so for the spin down case, so basically S will be equals to here 3, because it is 6 times 2, 6 times half equals to 3. Now the value of L. Now L is basically equals to, we know it is a summation over Lg. So first we will have a summation from the spin up, and then we will have a summation from the spin down. From spin up the summation will be 0, because all the states are filled. So this will be 0, and spin down we just have one case, one electron only. So that is also equals to +3. And then since 4F shell is more than half filled. Okay, since this 4f shell is more than half filled, so by Hund's third rule, J will be equals to mod of L plus S, so that will be 3 plus 3 equals to 6. Alright, then for each of these case we have to find a ground state, and ground state means we have to find the S, L and J value and also the symbol for this thing. So for symbol, how we write the symbol for the ground state. So for symbol, remember that the symbol case, how to write the symbol. The symbol is given by this formula 2s plus 1 capital L and J. Alright, so this is how we define the symbol for this LS, for this different atoms and ions, and atoms and ions according to their LS and J value. So this is the symbol that is used. And for this case L0, for L0 we write S, for L1 we write P, L equals to 2, you write D, L equals to 3, you write F, L equals to 4, S, P, D, F, then you just continue G, H, I and so on. Okay, you can just keep continuing it. Okay, S, P, D, F, then it is G, H, I. Alright, so now in our case we have S equals to 3, L equals to 3 and corresponding, okay, we have S equals to 3, L equals to 3 and we have J is equals to 6. So our symbol will be equals to the symbol which we are giving by this formula, that will be given by so capital L is 3, for L equals to 3 we have capital F, okay, J is 6 and it will be 6 plus and 7, so this will be our symbol 7F6. Okay, so this is going to be our symbol for this ion. Okay, then we go to the B part. Now for the B part we have ND3 plus, which has a configuration 4F3. So ND3 plus, it has configuration 4F3. Okay, so in this case again we have F, so for F, L is equals to 3 and thus the LZ value, it will go from minus L to plus L, so plus 3, plus 2, plus 1, 0, minus 1, minus 2 and minus 3. Alright, now we have to fill according to Hund's rule. First we will try to fill all the plus spin up electrons, and we have 3 of them, so we can fill up them wherever I fill these 3 spin up electrons, the energy will be the same. Okay, so the capital S value will be the same, so we need to maximize the S value will not change. So we go to the Hund's second rule, and Hund's second rule say that to maximize capital L we need to we want to maximize the capital value, and to do that we will start filling up from the positive L maximum value and then keep filling from the negative value. So we will fill 3 electrons like this, plus 3, plus 2 and plus 1. So now in this case S will be equals to, we have 3 plus half and we have 0 minus half, 0 for minus half, so that gives us 3 by 2. Okay, so our S value is 3 by 2. Then L value is just summation over LZ, so that will be equals to 3 plus 2 plus 1, so that will be equals to 6. Okay, I am putting a mod value here, but since we know we are filling them up according to the Hund's rule, so this L value is always going to be positive or not, it is always going to be non-negative, so no need to put this mod here. Alright, now since 4F shell is Now for the J value, we have to check how our 4f shell is filled. So since it is filled less than the half value means it is all the states are filled by at least one electron. Then that we call as a half filled. Okay, so if in this case it was all these we have like more than we have like 7 electrons, then that case is the half filled, because in total we can fill here 14 electrons. So if we had 7 electrons, then that is the half filled case. We will get one half filled case as well. Okay, and but in this case we have since 4f shell is less than half filled. So by Hund's third law, this G is given by L plus S. G is given by G is given by L minus S, mod L minus S. So that will be equals to 6 minus 3 by 2. So that will be equals to 9 by 2. Okay, it will give mod L minus S because it is less than half filled. So S will be equals to 3 by 2 here. L is coming 6. And G is equals to 9 by 2. Alright, and then the next thing is we need to find the symbol. So for symbol, remember the formula is L J to S plus 1. So here L is equals to 6, so corresponding to L equals to 6, we know that for the symbol we will have I. Okay, S P D F G H I. So L equals to 6, it is I. So we will have I. J is given 9 by 2. And this will be 2 as well. 2 times 3 by 2 is 3 plus 1 is 4. So this will be our symbol. 4I 9 by 2. Okay. Let's go to the C part. So for C part we have HO3 plus ion, which has an electronic configuration 4F10. Okay, again we have F, so L is equals to 3. So the LZ value or the ML value, you go to plus 3, plus 2, plus 1, 0, minus 1, minus 2 and minus 3. Alright, now we have, now first we will go with the first Hund's rule. We need to maximize the value of S. For that I will start putting the plus spin up electrons. Now because of the Pauli-Isolation principle, I cannot put any more spin up electrons. So now I have to put the spin down electrons. And now wherever I will put the remaining 3 electrons which will have a spin down minus half ms value, the capital S value will not change. So we will go to the second rule of Hund's, where we try to maximize the capital value of L. We will try to maximize the value of capital L. Okay, maximize the value of capital L. So for that we will start filling the electrons from the highest value of LZ or ML to the lowest value. Alright, so the spin down I will have 1 electron here, 1 electron here and 1 electron here. So remaining 3 electrons, we have already filled the 7, so remaining 3 will be filled like this. So here our capital S value from this case we have like 7 of the plus half spin up electrons, and the we have 3 of the minus half spin down electrons. So our S value will be equals to 2. Then the L value will be equal to summation of LZ, and we have summation from the spin up ones and a summation from the spin down ones. Spin up ones, they have half filled, so they will be 0. You can check their plus 3 plus 2 plus 1 and minus 1 minus 2 minus 3, sum up all, you will get 0. And for the spin down case, we will have we have filled it up to 3, 2 and 1. So this will give me 5, 6. L value will be 6. Now since again we can see that since 4F shell Now in this case, since 4f shell is more than half filled, okay, you can see that we have like seven electrons, more than 7 electrons are there, so it is more than half filled. Total we can fill 14 electrons, and we have more than 7, so half filled is when we have filled 7 electrons, and we have 10 electrons here, so we have more than so it is more than half filled. So 4f shell is more than half filled. So G is equals given by L plus S. So that will be equal to 6 plus 2 equals to 8. So we have S equals to 2, L equals to 6, and G equals to 8. So now we need to find our symbol for this case. Symbol formula, remember, it is Lg 2s plus 1. So here for L equals to 6, we will have symbol I, J is given 8, and just 2 to 4 plus 1, 5. So our symbol will be 5I8. Alright. Then the D part. In D part we are given carbon, and for carbon the electronic configuration is 1s2 is given, 1s2, 2s2, 2p2. Okay. Then so let's say so basically in this kind of problem, when you are given an electron configuration, first check that which of the shells are completely filled. So these shells are completely filled, so they have completely filled states. Alright, so they will not contribute anything to your SL and J value. Okay, so we don't care about these ones. All we care about is this one. Okay, because this is not completely filled. So we have 2p2. So for p, L is equals to 1. So our Lg value here, Lg will be equal to from plus 1, 0 and minus 1. So now again we will start filling the electrons. So we will follow our Hund's rule. So again according to Hund's first we need Hund's rule 1. We need to maximize the value of capital S. So we will start filling the spin up electrons. So we have 2 spin up electrons, so we can fill them up in several, like there are 3 C2 ways in which I can fill them up, and all of them will give the same value of capital S. Just 1 minute. Okay. Yeah. So like for the according to the Hund's first rule, we have to fill the spin up electrons. Okay, and we have 2 spin up electrons, so we can fill them up in any of these 2. Then we will go to rule number 2 to maximize the capital value of L. We need to put them from maximum value of Lz to minimum value of Lz. So we will put our electrons like this. So our capital S value now, that is given by, we have 2 spin half and 0 spin down. So our S capital S value will be equals to 1, and then the capital L value, that is given by summation of Lz, which is given by summation of Lz for the spin up and the spin down case. Now here this time the spin down case is 0 because basically we have no spin down electrons, so it will be 0, and summation over all these Lz values, we have plus 1 and 0, so it will be 1. And now since capital L is equals to 1, and since 2p shell is less than half filled, we will have J equals to mod of L minus S, which is equals to 1 minus 1 equals to 0. So we have S equals to 1, L equals to 1, and J is equals to 0 for our carbon atom. Okay. Now we need to find a symbol. Symbol given by Lg2s plus 1. So here L is equals to 1. For L equals to 1 we have P, symbol is P, J is 0, and it will be 2 times 1, 2 plus 1, 3. So our symbol will be 3P0. Alright. So let's go to part D. Sorry, this was part D. This is part E now, and this was D. Okay, then part E. So in part E we have oxygen now, which has electron configuration 1s2, 2s2, 2p4. So again we can see that these are completely filled, all of the states are completely filled. So S equals to L equals to G equals to 0 here in this case. And what we will have, we just need to consider this 2p4 case. Now for P, L is equals to 1. So we have Lg value will go from plus L to minus L. So we will have plus 1, 0 and minus 1. Okay. So first we will follow the first Hund's rule. We have to fill 4 electrons. So if I start filling the spin up electrons, I can fill all 3 of the this subshells, and then I have to because of Pauli exclusion principle, I cannot fill any more spin up. So I have to put spin down, and then we will go to rule number 2 now, because the S value cannot be maximized further. So the value of L should be maximized, and to maximize the L value we start filling from the highest value of Lz or Ml. So I will put my electron in the Lz equals to plus 1 subshell. So capital S will be equals to 3 times of plus half, and 1 times of 1 we have spin down electron. So that will give us 1. Alright. So capital S value is 1 here. Capital L value will be summation over Lz. So we will have contribution from the spin up ones and the spin down ones. Now spin up ones, they are completely filling the we have filled all the possible this spin up electrons, so that will give us 0. So what we'll have, and spin down is just put in plus 1 only one spin down electron is there. So a capital value will be equals to 1. Now for J we will go to the Hund's third rule, and now since the 2p shell is more than half filled, since the 2p shell is more than half filled, J will be equals to here, J will be given by L plus S, more than half filled, because it is half filled when there are 3 electrons, but right now we have more than, because maximum we can fill here 6 electrons. So half filled is when we have filled 3 electrons, and we have actually filled 4 electrons, so it is more than half filled. So J is equals to L plus S, which is just 1 plus 1 equals to 2. So we have S equals to 1, L equals to 1, and G equals to 2. Alright, and then we have to find the symbol. So symbol formula is L G 2s plus 1. Here we have L, for L we have S, L we have L equals capital L equals to 1. So capital L equals 1 can correspond to the symbol P, and G is 2, and it is 2 plus 1 3, because capital S is 1. So our symbol will be 3P2. Alright. So let's go to part F now. In F1 we have nitrogen atom. Okay, the configuration is 1s2, 2s2, 2p3. Right. Again the same thing. These ones are completely filled states. So this will give us S equals to L equals to G equals to 0, and we just need to consider for SLJ calculation. We just need to consider this ones. So now let's say now we have P L equals to 1. So we start filling these electrons. So Lz will be equals to plus 1, 0 and minus 1. Now we have to first we just follow the rule 1, which is maximizing the value of capital S. So all the electrons should be parallel and have the same spin, and we have 3 electrons only, so 3 electrons could be filled like this. So here we can see that this is a half filled case. Now this is the half filled case. Here S will be equals to, we have 3 spin up and 0 spin down. So S will be equals to 3 by 2. Capital L will be equals to summation of Lz. So this will be just from the from spin up and spin down if you want a contribution. So there are no spin down ones, so that will be 0. There are no spin down ones, and if you sum up this one, so this summation also comes as 0, because plus minus 1 equals to 0, so capital L equals to 0. And now since this P shell is 2P shell is half filled, so J, you can write J as mod of L minus S. So one thing that you should notice that whenever the system the system is half filled, then the capital L value will be equals to 0, because we are filling electrons from plus L to minus L. So by doing all the summation of this Lz, that summation will always be equals to 0. So for a half filled case, capital L is 0, and in that case both these two formulas, mod of L minus S and L plus S, both are just same, because L is equals to 0. But remember that there is a modulus L minus S. So that is given by, so J will always be equals to S, which is equals to 3 by 2 in the half filled case. Okay, so J will be equals to S. So this you can just remember, right? The note for half filled case, L is equals to 0 and J is equals to S. Okay, for a half filled case, L is equals to 0 and J is equals to S. Okay, for the half filled case. So now we have S is equals to 3 by 2. This is the half filled case. S is equals to 3 by 2. Then L equals to, so basically if you are given just one of the value, let's say if you are not given anything about the atom and just given that S is equals to 3 by 2 and it is half filled, then you know that you don't need anything else. Okay, you know capital L is going to be 0 and S is going to be equals to J. So no need for any calculation. J will be equals to just S in case of half filled, in the half filled case. So now the symbol in this case, in this one, okay, the symbol, the form Okay, we have to symbol means the formula Lg2s plus 1. Now this is given by, for capital L equals to 0, the symbol will be S, J is 3 by 2, and this 2s plus 1 will be 4. So the symbol will be 4s 3 by 2. Alright. So this was our problem number 6. Any doubts in this problem? So basically I guess I have covered almost all the possible combinations of Hund rules. So hopefully there will be no problem in doing this finding SLG now using the Hund rules. Hund's rules. Okay, now let's go to problem number 7. It is also, the next two problems, they are also related to Hund's rules only, but a little bit more we need to find using LSJ value, finding the other stuff using LSJ. So in the problem number 7, it is written that calculate the magnitude of the total magnetic moment and the around values of the magnetic moment along the field axis of an atom which has J equals to 1 and G equals to 2. Okay, so in this case nothing is given to us regarding the atom, only capital J value is given to us, and the Ronde G factor G factor which is G equals to 2, that is given to us, and it has asked us the total magnetic moment and the magnetic moment along the field axis. Okay, so for this problem, the magnitude of the total magnetic moment of an atom is given by, okay, so total magnetic moment, that is basically given by G under root of J into J plus 1, okay, times nu B, Bohr magneton, and the component of that moment projected along the field direction is minus G times capital MJ mu B, where this MJ value are similar to ML values or LZ values. So basically ML values or LZ values, they go from minus L to plus L. These capital MJ values, they goes from minus capital J plus J, where, let me just write, MJ goes from minus plus J goes as plus J minus 1 and so on, 0 to minus J plus 1 and minus J. So it goes from plus J to minus J by a difference of an integer. Alright, so now we just need to put here the values. Now when I guess I should have written this right. Okay, that's fine. So when J is equals to 1, is under root of J into J plus 1, that is equals to root 2, and the MJ value, okay, when J equals to 1, under root of J into J plus 1 equals to root 2, and the MJ values, they will be from plus J to minus J. So it will be minus 1, 0 or plus 1. Or you can write that they may go from minus J to plus J, so you can write, maybe this is better actually, minus J plus 1 and so on up to, so the values go from minus J to J minus 1 and J. minus g2 plus g. So minus 1 0 and 1, that will be your mj values. So therefore for g equals to 2, the total moment is 2. So the total moment is it will be just as given here, g times this, and g is equals to 2. So the total moment is just going to be 2 root 2 times mu v, and the component of the magnetic moment along the field direction can be minus 2 nu b, okay, because it is given by minus g times g is equals to 2, and mj is minus 101, so it will be minus mj times nu b. So minus 2 nu b, 0, or 2 mu b. Alright, and also you can see that here in all the field direction, okay, so we have a total magnetic moment, and then we have the magnetic moment, whatever the magnetic moment is along the field direction, okay. So this we can see that as you can see, the maximum value is 2 mu b magnitude wise, and magnitude wise the total magnetic moment is 2 times of 2 root 2 mu b. So note that in all cases the component along the field direction is less than the total magnetic moment. Alright, any doubt in this problem? Okay, so from this problem we just need to remember that the total magnetic moment is given by this, and the component of the moment projected along any of the field direction, that will be given by this, minus g times mj into mu b. Alright, so let's go to the last problem of this session. Alright, okay, so in this last problem, problem number 8, what is given to us for Fe, which is iron, the electronic configuration is given to us. So this way we have seen it in one of the previous problem as well. So first we have to write the electronic configuration for Fe2 plus iron. Alright, so part A, okay, so for part A we have to write the electronic configuration of Fe2 plus iron. So it is given that the electronic configuration of an Fe atom is, that is given to us as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, so here we have to do a plus 2 electrons. So generally so basically one might think that from where we have to take the 2 electrons. So here we should know that therefore because the transition elements give up their 4s electrons on they fold their 3d electrons on ionization. Okay, so remember that while filling the electrons, if you remember from your 12th standard or high school, basically when we fill the electrons in this transition atoms, then we fill up to the 3p6. Okay, if you have seen the periodic table, you fill up to 3p6, then you fill the electrons in the 4s one, and then you start filling up the 3d orbitals. Alright, so we fill the electron like this. So this electronic configuration that is given to us, that is the way we fill the electrons. If you have seen the periodic table, the atomic number, how the atomic number varies. Alright, so if we fill the 4s electrons, and then we fill the 3d shell. Okay, but when we do the ionization of these atoms, of these transition elements, when we do the ionization, then they give up the 4s electron first rather than the 3d. So if this kind of thing is given to us and then they ask the 2 plus, then don't make this mistake, like you have to take the electron from 4s rather than from 3d. So they give up their 4s electrons before their 3d electrons on ionization, because otherwise your answer will be completely wrong. Okay, so this thing you should remember. Ionization. Okay, so this is important. Okay, the transition elements give up their 4s electrons before their 3d electrons on ionization. Okay, so the electronic configuration of an Fe2 plus ion is 1s2, 2s2, 2p6, 3s2, 3p6 and 3d6. Okay, so that we have to take out 2 electrons, so we'll take out from the 4s shell. Although while filling, you fill the 4s first and then you move on filling the d shell, as you might have seen in the periodic table and your 12th standard as well, to write the electronic configuration. But in the transition elements, when you have to take out the electron, they goes from the 4s shell. So here again, because of this electronic configuration, we know that these ones are completely filled. So S equals to L equals to G equals to 0. So they will have no contribution from S, L and G. Now in the B part, it is asking us to determine the same thing, S, L and G in the ground state of an Fe2 plus ion. So in the ground state we need to find these ones. Now for Fe2 plus, from this above electronic configuration, okay, this we have basically 3d6 configuration. We have this 3d6 configuration. Now for D, we know we have done this, L is equals to 2. So we will have Lz value equals to plus 2, plus 1, 0, minus 1 and minus 2. Alright, then we have to fill 6 electrons. We will follow the Hund's rule. First we follow the rule number 1 to maximize the value of capital S. We can fill the 5 spin up. Now for spin down, wherever we put the capital S value doesn't change, so we go to rule number 2, maximize the value of capital L. And to maximize the value of capital L, we will start filling from the maximum value of Lz. Okay, because capital L is the summation over this Lz values. So I will put my spin down electron here. So capital S value will be equals to we have 5 plus half and 1 minus half. So S value will be equals to 2 in this case. So that's the same. That's the same thing we got for the iron atom case as well. as you can see, like for the iron atom, all the Fe2 plus ion, the S, L and J values, they are basically the same. Okay, so they are coming the same because the two electrons, they are going from the 4s shell instead of 3D. And then there will be the summation of summation of Lz, so that will be equals to you can see that will be equals to we will have two contributions, summation of Lz from spin up and from spin down. Spin up will give you a 0 because this is complete, the parallel spins are all filled, they have filled all the possible states, and Lg we have just one electron, that gives you plus 2. Now again, since the 3D shell is more than half filled, okay, so this is the same case as you can see, Fe and Fe2 plus they have the same S, L and J value. It is SL plus S, it is 2 plus 2 equals to 4. So our S value is 2, L value is 2 and J is equals to 4, right? So this is I guess this is interesting, like both your Fe and Fe2 plus will have the same answer. Fe3 plus, although it will change because then we have to take one electron from the 3D shell. Now the C part is calculate the okay, Randet G factor for Fe2 plus ion. So that is given by G equals to 1 plus J into J plus 1 plus S into S plus 1 plus L minus L into L plus 1 divided by 2 times of J into J plus 1. So this is the formula for Randet G factor, and then you can see that you can write this, okay, J plus 1 J upon J, J plus 1, you can subtract it from the denominator. So this you can write this formula as S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. Alright. So just put the values of S, L and J here. So we'll get 3 by 2, S is 2, 2 into 2 plus 1, 3, it will be 6, minus 6, divided by, we will have a 6 here as well because J is 4, sorry, so 4 plus 1, 5, 4 plus is more than half, is more than half, 2 plus 2 equals to 4, right? I guess I will written it here wrong. So it will be just 4 plus 1, 5 over 20. So let it be 40. J is equals to 4 here. Yes, 2 plus 2 equals to 4. Yes. So since S and J and S and L are same, so this will be equals to just 1.5. Okay. Okay, so this will be this 4, 2 times 4 plus 1, 5 here. Now note that since, just 1 minute, actually I want to put something more in this one, so just check. Okay, so we have so this is the G value. So G value is coming as 1.5. S equals to 0 case. If I have S equals to, just 1 minute, if I have S equals to 0. Okay, let's just, okay, so we are getting G value is 1.5. There was something I wanted to add, but let's not do that. Okay, so this was our part C, and part D is we have to calculate it again the total magnetic moment of an Fe2 plus ion and the magnetic moment along the field direction. So this we have seen the total magnetic moment is given by mu2 mu t is equal to g under root of g into g plus 1 and mu b. This is 1.5. This is 4 times 5, which is 20. Alright, this value is 20 mu b, and if you calculate it, this comes as 6.7 times of mu. This is the total magnetic moment, and then since g is equals to 4, mg value will go from minus j to plus j, so we'll have minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3 and 4. Therefore, the components of the magnetic moment along the field direction which is given by this minus g times mg into mu b can take the values. Okay, remember that the formula is minus g times mg nu b, so we have mg value and this mu of mg value, so that is given by, for like we have minus 4, minus 3, minus 2, which is given by basically minus g times mg into mu b. So these are given by for minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3 and 4. Right, so this will be given by if you put it is 1.5 times 4, it will be 6, and this minus will give you plus, so it will be 6 mu b, 4.5 mu b, 3 mu b, then 1.5 mu b, 0. Okay, this will be the corresponding values. Then we have minus 1.5 mu b, minus 3 mu b, minus 4.5 mu b, and minus 6 mu. So remember that in the formula there is a negative sign, right? It is minus g times mg into nu b. Just check in the formula. So we have done minus g times mg into nu b, right? So the field for the magnetic moment along the field direction for mg, whatever the sign of mg will be, the magnetic moment direction will be opposite of that. Alright, so this was our last problem of this session. Any doubts in this problem? Alright, okay, then we are already, it is 6 now, it is 6:05, so we can end this session. Are there any other doubts? Anyone have any other doubts? Alright, so if there are no doubts, then we can just end this session. Okay, thank you.